So we're going to finish off chapter 9 on water. Worksheets chapters 6 through 9 are due on the 2nd. That's after Thanksgiving, the Tuesday after Thanksgiving. Homework number 4 is due on the 2nd, again, the Tuesday after Thanksgiving. And your presentations and papers are due on the 4th. That's when we're going to start doing presentations in class. So make sure your topic's been accepted. I think I've got topics from pretty much everybody, maybe 1 or 2 people haven't. 2 to 3 page paper on the topic and a 5 to 10 minute presentation on the topic. The presentations will be in class, so make sure you submit your slides on Brightspace or have them ready so I can put them up on the computer here. So you can present in class. You can see the schedule up on Brightspace. It's in the semester project section. And then exam number 4 on chapter, yes? I'm going to be checking that they're long enough. I've never had a problem with people going over them. But yes, I will be checking that they're long enough, please. But it's going to be rough. I'm just going to be checking. Yes. And exam number 4 on chapters 6 through 9 will be on the 2nd. So we're going to finish up chapter 9 today. And I will start covering chapter 10 because we were ahead of schedule. I can cover a little more material, but chapter 10 will not be on the test or any of the homework, as you can see. And then next week we will have class on Tuesday, but not on Thursday because it's Thanksgiving. So, finishing off chapter 9, we had gotten to groundwater. So we talked about water on the surface. Let's talk about water beneath the surface. So one of the things that happens when you have porous ground is that it'll get saturated with water. The pore spaces underground get saturated with water. And this is the source of the largest freshwater reservoir for humans. This is our biggest source of fresh water. And it also acts as an important geological agent because dissolving by groundwater over the period of thousands to millions of years can produce sinkholes, caverns, and other things. In some places, this collapse from removing groundwater can be quite impressive. You can have subsidence from removing groundwater. You can have sudden sinkholes appearing when you remove groundwater that was helping support an empty place, a place that had been worn away by dissolving and such. This is a big problem in Mexico City because they built that city on a swamp and then they cut off the resupply of groundwater to it and have been steadily pumping out all the groundwater. It's having some unfortunate side effects. Yes.
I thought Chicago was also built on a swamp.
Chicago was built on a swamp. Mexico City was basically built on a lake. And the way they paved it and such cut off the resupply of water to it. Because it's just like a basin surrounded by mountains. And they cut off a lot of the places where it was getting water. So it didn't feed back in. It was a lot wetter than, lots of cities were built on swamps. Chicago was built on a swamp as well, yes. And we have issues with groundwater. But we also don't have issues with losing resupply because the lake is right there. But a lot of the areas that were feeding water into the groundwater of Mexico City got cut off. by development, being paved and such. And they pumped out a lot of the groundwater, which we in Chicago didn't really do because we just get fresh water from the lake. But yes, Chicago was built on a swamp. And you know, there was a point where we raised the city several feet to, well, install sewers actually. But so yeah, if you want to see some interesting things about how much of a soggy mess Chicago used to be, the River Museum, which is at the Chicago River in Michigan Avenue, I think. It's in the bridge tower. Has some interesting stuff. It's free, so. Actually, I don't know if it's open. It opens at the summer. So the subsurface pore stations, yeah. It also acts as an equalizer for stream flow. So water can seep out of streams into the groundwater and into streams from groundwater, and it helps even things out. So most of the fresh water on Earth is frozen. But of the not frozen water, groundwater makes up the vast majority of it. It's 96% of all liquid fresh water is groundwater. It's underground. Because there's a lot of space underground for it to go, basically. So there are underground zones. As you go down from above, near the surface, there's more air in the soil, and as you go deeper, it fills more and more with water until you hit a point. So there's a belt of soil moisture where there's both water and air, and then there's a point where you hit the zone of saturation. That's the point where all the pores are full of water. And water within these pores is what's known as groundwater, and the top of the zone of saturation is the water table. Around here, the water table is very close to the surface. Don't have to dig very deep to hit the water table. And you know you've hit the water table if you dig a hole and water starts to seep in from the bottom of the hole. You've hit the water table. And since we're so close to the lake, and we're so close to the level of the lake, we don't have to dig very deep to hit the water table. Now, a spring is a point where the water table hits the, breaks the surface at some level. So you can have several different ways that. So here's the main water table. Here we have a perched water table where we have some material here that's an aquitard. It doesn't let water through. So water is settled down on top of it. There's water on top of it that you could extract, and there are springs happening at the end where it hits the edge of the ground and feeding down into the main water table. This is the main water table. So we have an unsaturated zone above and a saturated zone below. Here we have a well that wasn't dug deep enough, so it's not successful. And the water table will flow, it could have a flow down towards streams and such as it feeds these streams. Now, the distribution of groundwater depends on a couple of factors. There is porosity, which is how much empty space is in the ground. Some rock is more porous than others. It's got more holes in it. It determines how much water can be stored in that earth. The amount of storage of groundwater. But another important factor is permeability. You can have a lot of porosity, but a very low permeability, where there's space for water to be, but it can't flow. So permeability is the ability to transmit water through connected pore spaces. An aquitard is an impermeable layer of material. It's a layer of material water can't pass through. Things like clay, certain types of very dense rock, stuff like that. An aquifer is a permeable layer of material that you can draw water from, and water will flow through. So you could put a well into an aquifer to get water. And a demonstration of porosity, you could have, if you have on the left, you have 100 milliliters of dirt, sediment, 100 milliliters of water. If you pour water into this sediment-filled beaker, you can pour like 500 milliliters of water in there. Half the space is pores. So half the space in that loosely consolidated sediment is pores, is space that can be filled by water. So that can be the case for rock as well underground. I mean, maybe it's not 50%, but you could have a significant amount of water underground. Now, a well is a way to access that groundwater. I mean, the oldest fashioned well is just a hole. You dig a hole until you're deep enough that your hole reaches below the water table, water flows into your hole, and then you can pull water out with a bucket on a string. You know, that's a classic fantasy looking well. Now, more modern wells, we pump the water out with pumps. So pumping on a well, we drill a hole down till it's well below the water table, and we pump water out. Pumping can cause a drawdown or a lowering of the water table around the well, because you're removing the water at the side of the pump, and it takes time for water to flow in to replace it. So if you're pumping water out faster than it can flow in, the water table around the pump will lower. And this can form a cone of depression in the water table. You have water, the water table sinks at the pump, and that sort of spreads out in a cone around. So if you have a really hungry source of water, like, I don't know, big agricultural site using lots of water, or somebody bottling water for profit. Nestle bottling water for profit or something. But if you have a big user of water that's pumping a lot of water out of the ground, it can actually lower the water table around that well enough that it causes shallow wells nearby to end up going dry. You may have also heard of artesian wells or artesian springs. Artesian wells. Artesian wells are wells where you don't need to pump. These are wells where the water is trapped beneath some impermeable layer and is fed, and the actual water table is higher than the surface of the earth above them. So, or at least the initial groundwater level. So for an artesian well, the classic artesian well, you drill a hole down and water springs forth because it's being fed, because there's a layer, there's like 2 layers of impermeable material. The water is trapped beneath, and they're being fed by some source that's uphill, above where your well is. So for an artesian spring, for an artesian well to happen, it has to be confined by an aquitard. So here's an example of the cone of depression. We have a large agricultural source using lots of water with high capacity, and it causes nearby wells to go dry because of heavy pumping. Cause this cone of depression. But an artesian well is between 2 layers, and so the pressure causes it to rise up out. And that's why we build water towers. We build water towers to do the same thing that artesian wells do naturally. We create water pressure by moving water up high and just letting the natural process of pressure go. So here's a short video about cones of depression caused by overuse of deep wells.
Groundwater cone of depression. The depth of a water table is frequently changed when groundwater is pumped from a well. Groundwater flows toward a well, so over time, the level of the water table tends to slope down toward the bottom of the well shaft. Notice that as the two wells pump groundwater, the level of the water table falls until it resembles a downward-pointing cone around each well. This is known as a cone of depression. A cone of depression will grow larger until the rate of groundwater recharge matches the rate of groundwater pumping. Notice that the cone of depression in the water table around the more heavily used well grows larger than the cone around the less heavily used well. The cone of depression around the heavily used well eventually grows so large that the water table drops below the level of the shallower well, which then goes dry.
So, if you really hate your neighbor, it's possible to dig a deep enough well and pump enough water to cause their well to go dry. I wouldn't do that. You'd probably get sued. But so an artesian system is one where it's the water aquifer is trapped beneath some aquitard and fed by a recharge area that's at a higher altitude. And so the natural pressure surface where the water would settle is above ground level. So when you drill a well, the water will naturally flow out of that well. And that's an artesian well. And we artificially create the situation of fed by a higher pressure surface that's high in the air with water towers. Water towers provide water pressure to large areas by moving water up into the water tower to sit there and feed in to people's homes. So this is about an artesian systems.
Hello, this is Callan Bentley. Welcome back for another Smart Figure. After watching this video, you should be able to describe what an artesian system is and distinguish between flowing and non-flowing artesian wells. This is an example of a flowing artesian well. Basically, all you have to do is drill a hole in the ground, and then coming up out of that hole, boom, is water. It kind of reminds me of the opening sequence of the Beverly Hillbillies, where Jed's out hunting rabbits, and he shoots his rifle, and the bullet pierces an aquitard, and that aquifer underneath holds not water but oil, and it starts oozing out onto the ground. It's the same thing here, except groundwater is what's flowing out of this hole. So let's take a look at two examples of these artesian wells. We're going to take a look at one that's very close to the recharge area, and then we're going to take another look at a second one that's further away from the recharge area. So let's go ahead and take a look at the first one here. We're going to zoom in on this area. You can see here that we've got an aquifer that's confined by two aquitards, one above and one below. You can see that the top of the groundwater there is the water table, and if you extend that water table off to the right, imaginarily through the aquitard that overlies the aquifer, that is what we call a pressure surface. And if you were to drill a well down and pierce that aquitard, the water would flow up in that well to that pressure surface. So the pressure surface is above the top of the aquifer, but the pressure surface is below the ground. So as a result, this is a non-flowing artesian well. Contrast that with this situation. This is more like the example that we looked at to start with. Further away from the recharge area and at a lower elevation, the pressure surface is actually above the surface of the earth. As a result, the water in the confined aquifer wants to flow up through that well to reach that pressure surface, but basically it's hitting empty air there, so it ends up flowing out over the landscape. Gravity is more dominant than the pressure that's driving it out. This is the same exact principle we use basically to create water pressure in our houses. You know that there are these weird water tanks that are rising over the landscape in various places like UFOs. Basically what we do is we pump water up into those water tanks, and then that creates an artificial pressure surface. Then when you open the tap in your house, say to take a shower, the water flows out of that tap because it's trying to reach this pressure surface. Of course it never gets there because we don't let it flow out in high enough volume, and there's a lot of empty space for it to fill up before it ever got that high. That's why water comes out of your shower head when you turn the knob. Here's an actual example in South Dakota. Basically, we're going to take a look at a cross section from west to east across South Dakota, and you can see the Black Hills over on the left and the flat area of the Great Plains over on the right. So what we've got here is the Dakota sandstone, and this is an example of an artesian system. And basically what I'd like you to do is imagine what the pressure surface must look like in order for this area over here to be an area of flowing artesian wells. Well, okay, you had a minute to think about it. Probably what that pressure surface looks like is something like this. So it comes out over the landscape like that. And so if you're to drill a well here, piercing through this Cretaceous shale into the underlying Dakota sandstone, the water that is entering the Dakota sandstone from over here on the flanks of the Black Hills is going to try and flow up those wells and reach that pressure surface. Hopefully you got that correct. Thanks very much for your attention. This has been another Smart Figure.
So artesian wells are wells where the water at least partially rises up above the initial surface where you hit it. And flowing artesian wells are ones where it makes it to the surface. You can have springs. Springs are places where water naturally comes out of the ground. Hot springs are places where the water has passed through some geologically warm area. The water is 6 to 9 degrees Celsius warmer than the mean air temperature of the locality. These are generally heated by the cooling of igneous rock. There was some process that caused hot, magma to rise up nearby. Its steady cooling has released heat into the groundwater, which warms the hot springs. Geysers are intermittent hot springs. There are chambers where water turns to steam and erupts outwards violently. Yellowstone National Parks don't have a lot of these. The Yellowstone National Park is sitting on top of a magma hotspot. So there's a lot of heat rising up there. So this is Old Faithful in Yellowstone. It's a very regular one of these geysers. If there's a chamber that fills with water, that water eventually gets hot enough to basically boil and explode upwards as steam. And some of it boils and explodes upward as steam, causing this burst. Now, there are a number of environmental problems related to groundwater. One of these is not treating it properly with regard to it as a renewable resource. So groundwater does renew, but it only renews so fast. So if you consume it faster than it renews, that's a problem. Another is that you get land subsidence caused by its withdrawal, because that groundwater is filling all that porosity, all those holes. If you take the water out, well, now there's a lot of air there and it can collapse and settle. So this is a big problem in certain places. The Central Valley of California has subsided like 50 feet or something because of all the agricultural use of water. It's a similar problem in many other places where there's a lot of groundwater being pulled out. I hope it. I was some city that was having a real city. Oh no, yeah, it's Indonesia. Some of the horrible corruption screwed up the water system, and then everybody started drilling their own wells, and now cities are big portions of city of like Jakarta are sinking because they contaminated their proper water supply because they privatized it. And contamination is a real issue. If your water supply is contaminated, you can't use it. If you have pollution that gets into the groundwater, it can take a very long time to go away, because groundwater doesn't move very fast. So groundwater supplies are a limited resource. I mean, they do recharge, but they only recharge so fast. So water tables will drop during dry seasons, and it will also drop if the rate of extraction through water wells is higher than the rate of recharge. So in order to maintain a stationary water table, water must be replaced into the aquifer at the same rate that it moves out of the aquifer. And recharge is the rate of water replacement into an aquifer. And the source of recharge is, rain. It's precipitation and flowing streams at the surface help feed in, soaking into the ground, feeds the aquifer. And if you pave all the surfaces, then the water doesn't actually flow into the ground. The real issue. And meanwhile, the aquifers are being depleted due to very high extraction rates. So the Ogallala aquifer in the central US is a good example of aquifer depletion. This aquifer received most of its water about 10,000 years ago during the wetter climate of the last ice age. And the natural recharge of this aquifer can't keep pace with the over 150,000 wells that are constantly extracting water for agricultural use. So some of the biggest users of water and groundwater is agriculture and industry. And one of the things that can happen as you pump out water is subsidence. So water within the zone of saturation helps support the earth around it, and it supports the overlying weight of the strata, because water doesn't compress. And so as the zone of saturation shrinks, the overlying strata begins to compact, the porosity reduces, and the ground surface subsides. And ground subsidence can lead to shifting in building foundations, ruptures of pipelines, cracks in roads, and in low-lying coastal areas, it can lead to flooding. So here's an example of that subsidence since 1925. 30 feet of subsidence over 52 years of heavy pumping in California's Central Valley, the San Joaquin Valley. So this is how far it's sunk since 1925. And that's in 1977 when this was taken. It's probably worse now. Groundwater contamination is another issue. So in most coastal areas, the groundwater is separated by density. You have fresh water on top of salt water. Because fresh water is less dense than salt water, and it therefore tends to stay on top of the salt water. And because they're all in the ground, which doesn't have a lot of room for mixing, they don't mix that much. But excessive withdrawal of fresh water can result in salt water being pulled up into the wellbore. And once the salt water is there, it's not leaving. So if the denser salt water gets pulled up, the water well will be ruined and the level of the water table will change. So you can have, so normally you have fresh groundwater and then salty groundwater from the ocean. And then if you excessively pump, you can end up pulling up the salty groundwater and contaminating your well. And the salty water is not, the fresh groundwater is not really going to flow back in. You're just going to resettle with a new equilibrium where the salty water is a higher level. So pollution is a real issue, but numerous problems will arise when you have too much water extracted or the extraction rate is too rapid. Water tables get lowered, ground subsidence occurs, saltwater contamination is possible in more coastal areas. And so the proper management of groundwater reservoirs is critical. And also groundwater contamination occurs when other substances that we would not like in our water percolate down into the zone of saturation. These are things like industrial and household chemicals, pesticides, fertilizers, sewage, herbicides, detergents, refined petroleum products, and others. And the nature of the porosity and permeability of the ground can affect how this works out. If you have a place where groundwater moves quite slowly, and you have, say, sewage contamination, given enough time underground, will be dealt with by natural bacteria. So if groundwater flows slowly, then you might be fine with a well relatively nearby. But if it flows too fast, then you won't be. So a lot of it depends on location. So water quality can be adversely affected depending on the pollutant and the concentration present into the groundwater. And some pollutants will, given enough time, will be handled by nature. Some won't. A lot of the nasty industrial stuff like heavy metals and things like that never go away. Gotta clear them out some other method. So here's an example comparing two aquifers. Here we have an aquifer with very permeable cavernous limestone karst. So if you have a septic tank over here, the contaminated water can very easily flow to a nearby well. More than 100 meters, though the contaminated waters travel more than 100 meters before reaching well 1, it moves too rapidly through the cavernous limestone to be purified. It doesn't have enough time for the natural bacteria to break down all the contaminants. However, here, if it's percolating through permeable sandstone, it moves much more slowly and is purified in a relatively short distance. So you need to understand the ground around you with things like that. And you can design your system to ensure that that occurs. Now, groundwater also does geologic work. Groundwater is slightly acidic. Usually, it contains weak carbonic acid that comes from the carbon dioxide in the air, carbon dioxide released by bacteria in the soil. It can contain other acidic compounds from stuff in the soil being released by things in the soil. And that weak carbonic acid can dissolve the calcite in limestone. This can form caverns, because caverns are formed by dissolving rock beneath Earth's surface. Well, that's one of the ways that caverns are formed. It's the most common way. And these caverns are formed in the zone of saturation. Now, the water table may then move, and the caverns may end up dry. But a lot of these are formed where they're wet, where things are wet. You get caves and caverns formed by methods that don't involve groundwater as well. Like one of the ways you can get is lava tubes. So when lava flows through a tube, it flows out, it can harden around the outside of the channel it's traveling through, but the inside can empty out, and you can get caves formed that way. Caves and caverns formed that way. But caverns are formed, but the most common way we get caverns are limestone caverns, limestone caverns formed by dissolving rock beneath Earth's surface, and these are formed in the zone of saturation. There's a number of features found within caverns that will form within the zone of aeration. So once the water table drops below, there's still water passing through these. There's water coming from above passing through the caverns. These can form, that water was dissolving limestone. Then as it enters into the caverns, it's going to start to evaporate. And as it evaporates, it will deposit some of the calcite in the cavern, forming what is called dripstone. So the calcite is deposited as dripping water evaporates. Some common features of dripstone include stalactites, which hang tight from the ceiling, stalagmites, which grow up from the floor. There are certain things that can happen on the walls as it flows along the walls. There are structures that form there. But yes, these are dripstone. So here's a very thin, like tube with water forming. As the water evaporates at the surface, the calcite precipitates out and forms the structure. Here are stalactites and stalagmites. You can get columns formed. You can have weird lumpy structures on the walls. These are things that form in caves, but these structures need air to form because they're formed by the evaporation of the water. And when you have this limestone being dissolved and carried away, this forms what's known as karst topography. And it's a surprisingly common form of geology. It's formed by dissolving rock at or near the Earth's surface. You get lots of caves and caverns. You often get sinkholes, these surface depressions where caves and caverns collapse, fall inwards. Sinkholes formed by dissolving bedrock and the caverns collapse. And you have caves and caverns. Often the area lacks good surface drainage. So during early stages, groundwater will percolate through limestone along joints and bedding planes, and solution activity will create in the large caverns at and below the water table. And with time, the caverns will grow larger and the number and size of sinkholes will increase. And surface drainage is frequently funneled below ground. And as caverns collapse, and the coalescence of sinkholes will form these larger flat-floored depressions. And eventually solution activity may remove most of the limestone from the area, leaving isolated remnants as in figure 9.44. Do I have that picture in here? I think I do not, but I can pull it up. You can quickly pull that up. Go ahead. Yeah. Nope, that's chapter 10. Oops. So I don't have a convenient. I can't pull it up. But, I mean, the most extreme is you get these sort of pillars remaining. So in Southeast Asia, you can see these sort of pillar islands. You get these bays with pillar islands in them, where most of the ground was gone. I mean, you can look up 9.44 in your text. So the chemical weathering of limestone is caused by carbonic acid. It comes in contact with calcite in limestone and they react. And so carbonic acid plus calcium carbonate forms calcium bicarbonate, which readily dissolves in water and then gets carried away in solution. And most chemical weathering in limestone occurs along fractures where the most water flows. And given enough time, underground caverns form. And then these caverns can collapse, causing sinkholes. And here are a couple of examples. So this is some examples of karst topography in Illinois.
Hi, my name is Sam Pano. I'm with the Illinois State Geological Survey, and I'm a senior geochemist under the Prairie Research Institute, which is part of the University of Illinois. And in my job, I do a lot of investigations of karst areas, and I should probably tell you what karst is. About 25% of the world sits on karstified carbonate rock, like limestone and dolomite. And in Illinois, 25% of the bedrock is limestone and dolomite, with about 10% of the area having karst features. If you have carbonate rock, which is soluble in rainwater, it dissolves in rainwater, soil water, and so on. So basically, all the rocks, all the bedrock in Illinois and the entire world are fractured to some extent, And when the rainwater seeps in, or surface water, it begins to dissolve this rock. The process takes thousands of years, tens of thousands of years, millions of years. What occurs is the fractures get bigger and bigger. Then the water can seep into the bedding planes, just fairly flat-lying layers of limestone, and create caves. And the caves can be quite extensive. For example, in southwestern Illinois, there are caves that extend for 15 miles with passages that are 30 feet in diameter and rivers running through the cave. So this is the kind of areas we study.
And then here's an example of a dramatic sinkhole occurring in Louisiana.
Oh yeah, you said
They move it, John.
Yep, I got it.
Coming to the sinkhole.
Look, right
I
here,
got
you
it.
can see it. It's moving that much. Oh, that's gone right there. See it right there? Look at it.
Breathe forward. Go on all in. Oh, that's a good one. Look over there, John, on pad 3.
Well, let's get a read.
All right.
We had a 1 foot wave headed that way. Back in the
Let me see if I can pull up that image. So here's an example of what you can get with extreme cases of karst topography. You just get these pillars remaining of slightly more durable landscape. You can also have massive sinkholes like you see here. Let's continue on to, so that's the end of chapter 9, which is the end of what's going to be on the test. Everything else here is sort of extra. So let's continue on to chapter 10 about glaciers, deserts, and wind. Some of the other forces of erosion that exist. And around here, in fact, when glaciers were one of the most important factors that led to the landscape around where we live, because this whole area was basically scraped flat by the glaciers from the last ice age. So we'll talk about the role of glaciers in the hydrologic and rock cycles. We'll describe different types of glaciers, their characteristics, and their present-day distribution. We'll talk about how glaciers move, the rates at which they move, and the significance of the glacial budget. We'll discuss the processes of glacial erosion, identify and describe the major topographic features sculpted by glacial erosion. We'll distinguish between the two basic types of glacial deposits and briefly describe the features associated with each type. We'll explain some important effects of the ice age glaciers other than the formation of erosional and depositional landforms. We'll discuss the extent of glaciation and climbing variability during the Quaternary Ice Age. We'll summarize some of the current ideas of the causes of ice age. We'll look at the distribution and extent of Earth's dry lands and the role that water plays in modifying desert landscapes. We'll discuss the stages of landscape evolution in the basin and range region of the western United States. We'll talk about the way that wind transports sediment and the features created by wind erosion, and we'll explain how loess deposits differ from deposits of sand and discuss the movements of dunes and distinguish among different dune types. So glaciers are part of both the hydrologic and rock cycle. They're part of the hydrologic cycle because they're made of water, ice, but water, and they're part of the rock cycle because they can carry rocks with them and they erode and transport sediment. So a glacier is a thick mass of ice that forms over land from the compaction and recrystallization of snow. And it shows evidence of past or present flow. Basically, glaciers happen when more snow falls than melts. So if you have some place where more snow falls in a year than melts, that snow will start to build up, compress, and recrystallize to form glacial ice. So there's several types of glaciers. Valley or alpine glaciers form in mountainous areas. Here's a valley glacier flowing down a valley. Ice sheets or continental glaciers are large scale. The current places on Earth with ice sheets are Greenland and Antarctica. These formed during the last glacial maximum 18,000 years ago. And we can also look at the difference between sea ice and ice shelves. There are also other types. There are ice caps and Piedmont glaciers. So here's a video about the ice sheets. So currently there are two ice sheets. There is and the Antarctic ice sheet and the Greenland ice sheet. And then there are ice shelves, which is where that ice sheet goes over water. And then there's sea ice. There's lots of sea ice around the North Pole part of it. So here's a video about ice sheets. So here are the Greenland ice sheet.
Scientists have been probing the Greenland ice sheet from the ground, air, and space. Now a new study uses those observations to see within the ice sheet, laying bare a tale more than 100,000 years in the making. When we look inside an ice sheet, we can see distinct layers formed by thousands of years of snowfall. As snow accumulates, these layers get progressively compacted into ice, which then flows under its own weight. To get a precise history of a particular spot on an ice sheet, scientists drill into it and recover ice cores, which provide a record of the ice's age and what the past climate was like. Seasonal variations, along with ash from volcanic eruptions, show up in the cores, allowing us to date the ice and correlate samples from different sites. To extend this age information across the ice sheet, the best tool that we have is ice-penetrating radar, mounted on aircraft flying low over the surface. Radar transmits electromagnetic pulses into the ice and records the reflected signals, allowing us to track the depth of the layers detected in the ice. Since 2009, NASA's Operation Icebridge has flown over Greenland more than 100 times with a wide variety of instruments, including radar, and produced vast quantities of data, adding to the work from many other missions. This has allowed researchers to generate a three-dimensional map depicting the age of the ice throughout the Greenland ice sheet. This 3D age map shows that 3 distinct periods of climate are evident within the ice sheet. The Holocene, shown here in green, the last ice age, shown in blue, and the Eemian, shown here in red. The top layers from the Holocene period formed during the last 11.7 thousand years and are fairly flat and uniform, though the thickness varies depending on how much snowfall occurred. Below this, deeper within the ice sheet, we see layers that formed during the last ice age. Layers from this period are darker and more complex, having been further squeezed and sometimes folded as they flowed over the rugged bedrock below. Deeper still are layers of ice left over from the warm period before the last ice age, more than 115,000 years ago. Eemian ice can reveal how the ice sheet responded to a period of warmth similar to the one we are experiencing today. Several ice cores have recovered Eemian ice, but it is difficult to interpret. This new map of the age of the ice sheet shows that there is more Eemian ice than expected in northern Greenland, where it may be easier for scientists to collect and analyze. This new analysis reveals a 3D map of the age of the Greenland ice sheet, from the oldest Eemian ice, to the layers deposited during the last ice age, to the ice that formed during the Holocene. The response of the ice sheet to past climate change led to its current age structure. Further study will help us better understand how the Greenland ice sheet will respond to today's changing climate.
One of the reasons that ice cores are so useful for studying climate data is that glaciers are made of snow. Snow is full of air, so they actually trap little bits of air in them as they compress to form glacial ice. So you can actually get samples of the atmosphere from thousands of years ago that have been trapped in the ice. Now, glaciers move by flowing under their own way. They have plastic flow where they distort, and they also slip along the ground, slide along the ground. And in the uppermost 50 meters, they have a zone of fracture where crevasses will form in the more brittle ice that's under less confining pressure. Much like how with rock, near the surface, you get more cracking and fracture. Deeper down, you get more plastic flow. So here are some crevasses in a glacier. And in a glacier, there's a zone of accumulation, which is the area where the glacier forms. This is the area where more snow settles than melts. Then there's a zone of wastage. This is the area where there's a net loss due to melting or calving, which is when chunks of ice separate off into the ocean. And the glacial budget is the balance between accumulation at the upper end of the glacier and loss at the end. So in an alpine glacier, in a valley glacier, you generally have snow accumulating at the top, flowing down and melting at the bottom, feeding into very cold alpine streams and lakes and such. So the zones of a glacier, you have a zone of accumulation at the top, where more snow falls each winter than melts each summer. This flows down to the snow line, which is the point of equilibrium. And then at the bottom, you have the zone of wastage, where all of the snow from the previous winter melts along with some glacial ice. So up here, more snow falls than melts. Down here, more snow melts than falls. So this is a short video about that glacial budget, the balance between accumulation at the top and loss at the bottom.
Hello, this is Callan Bentley. Welcome back for another Smart Figure. After watching this video, you should be able to describe what influences the glacial budget. Glaciers flow downhill. This is an important realization to have in this discussion because we're going to watch the front of the glacier, the downhill end called the terminus, and that terminus is going to move, and it might move downhill or it might move uphill, but all the time the glacier is flowing downhill. The glacier has two regions that we need to pay attention to. Uphill is the zone of accumulation where more snow falls each winter than melts off each summer. At the bottom end of the glacier is the zone of wastage, where all the snow from the previous winter melts, as well as some of the glacial ice itself. So whether the zone of accumulation ends up gaining more snow each winter, or whether the zone of wastage ends up melting more glacial ice each summer, ends up determining whether or not the glacier ends up growing or melting back. One form of wastage is simply melting, where the ice turns to water. Another form of wastage is what's called sublimation, where ice directly goes into the gas phase. That happens in really dry regions. And then there's also the possibility of calving icebergs. So some glaciers flow out to sea, and there they form ice shelves, and those ice shelves can break off, generating icebergs. The process of generating icebergs is referred to as calving. What would happen to a glacier which experiences first an increase in its glacial budget? In other words, the zone of accumulation gains more than is lost at the zone of wastage, and then undergoes a reversal of fortunes where the zone of accumulation ends up gaining less snow and the zone of wastage ends up losing more. What would end up happening to that glacier? Okay, you've had a moment to think about it. So I think first off, you would end up seeing that the glacier would advance because, again, there's more going in at the top end than is being lost at the bottom end. So the glacier grows. It might end up depositing a nice end moraine there as it grows. And then comes the period of time where there's less being added in than is being lost at the bottom end. So there's less accumulation and more wastage. At that point, the glacier is going to retreat. So the terminus of the glacier is going to back up, even though the glacier itself is flowing down the mountain the entire time. A new end moraine will be generated. And then, of course, the glacier might end up melting off entirely. And just by looking at the position of those two end moraines, we can end up deducing its history. Thanks very much for your attention. This has been another Smart Figure.
So when glaciers retreat, they leave behind, end moraines, piles of material where they were settling up, material that had been eroded along, which you can trace. But here's an example of a retreating glacier, where in 1935 it was filled the valley, and now you can see the valley is instead filled with snowmelt. Now glaciers erode material as they move. They pick it up. They can erode by a couple of ways. They can pluck things up. They can just lift up blocks of rock and carry them with them, or they can abrade rock off of various surfaces. This can create rock flour, which is pulverized rock, and striations, these grooves in the bedrock. And one of the things about glaciers is that when material is carried through streams, it gets sorted and it gets worn down, becomes rounder. When material is carried by glaciers, it doesn't get sorted at all, just gets picked up and moved until the glacier melts and it dumps it out. So there's no sorting glacial till. So here are some examples of glacial abrasion. Here are these scratches and striations caused by a glacier. Here's an area with glacially polished granite in Yosemite National Park. Here are these grooves from glacial abrasion on the scratches in this bedrock. And landforms created by glacial erosions. You can have a glacial trough. You can have a hanging valley. You can have a rounded structure called a cirque. You can have an arete. You get near these cirques, you get these distinctive mountain peaks called horns. And where glaciers end, you get fjords. So here are some of the structures. Aretes are these sharp edges here. You get very distinctive peaks called horns. Cirques are these sort of circular valleys worn out in the zone of accumulation, where material builds up, and you get these V-shaped. So in unglaciated topography, you get V-shaped valleys, where you have glaciers, you get more U-shaped valleys. So this is a glacial trough. You could have these hanging valleys where they're, the trough is, they don't, naturally feed into each other. There's this big drop off. So these are some uniquely glacial topographies. So here are some erosional.
This is Callan Bentley. Welcome back for another Smart Figure. After watching this video, you should be able to identify and describe erosional glacial landforms that occur in areas of alpine glaciation. Here's a look at an area of alpine glaciation. This is PHY Lake in the Canadian Rockies, and you can see a bunch of awesome glacial features here. You'll note the U-shaped valleys that are very prominent in this image, including some small ones that feed into the larger ones. Where those U-shaped valleys intersect, you end up getting these sort of knife-edge ridges, and you see a pointy little mountain here in the background. The lake itself is a glacial feature. Let's take a look at all of these. So the Canadian Rockies probably started off as a landscape that would look something like what you see in this picture. There would be stream-cut valleys, which have a V-shaped profile. But then the climate got colder, the valleys filled with snow, the snow packed into ice, and the ice began to flow. This made glaciers, and those glaciers eroded into the rock that they flowed over, and they carved it into new shapes. After the glaciers melted away, those shapes remained, and you can see some of them here. Here's that pointy mountain with the faceted sides. That's called a horn. The sort of amphitheater-shaped features up at the top of these small valleys are referred to as cirques, because they kind of call to mind a circus or a circle. If you find a small lake in a cirque, you might call it a tarn. If one tarn flows into another, which flows into another, that whole string of lakes is referred to as a set of pater-noster lakes. And then, of course, there's the main glacial valleys themselves, which are U-shaped. The intersection of those U-shapes can produce the knife-edge ridges known as aretes, and where the aretes abruptly truncate against the main glacial trough, you see truncated spurs. Let's take a look at what happens where a river flows out of a hanging valley and into the main glacial trough. That ends up frequently producing spectacular waterfalls, like this one here in Yosemite National Park. See the U shape of the hanging valley that hosts that river? That U-shaped theme appears again and again. Here's a cirque, and you can see that it is U-shaped in profile. And then up above is an arete. You can see the edge of one U-shaped valley leading up to that arete. If you were to draw what this arete looks like from a cartoon kind of perspective here, you've got two U-shaped valleys intersecting with one another, and the pointy knife-edge ridge that separates them is referred to as an arete. Let's see what we can identify here in this picture. This is looking at an alpine glacial landscape, and you can see some of these erosional features. Hopefully you notice the U-shape to the valleys. You can also see here's a little tarn, and it looks like there's a drainage that goes into another little tarn, which goes into this bigger tarn here. That would be a series of pater-noster lakes, okay, like beads on a string. Off in the distance here, you can see the knife-edge ridge of an arete separating one glacial valley from its neighbors. And there's some mountains in here that have vaguely faceted slopes, not really classic-looking horns, but perhaps you could call that a horn as well. All right, nicely done. Hope you identified those features. There are many more to be found in your textbook. Thanks very much for your attention. This has been another Smart Figure.
Okay, we can stop there for today. We'll continue on with chapter 10 on Tuesday. And So we will meet Tuesday next week, but obviously not Thursday because that's Thanksgiving. So I'll see you all next week. Yeah, have a nice day.